Now let's look at the kinematics of particles. So if you'll remember from the previous video, the kinematics has to do with the motion of a particle without considering forces. So we only care about the position, the velocity, and the acceleration of our particles. We're not too worried about how they got the energy to do the motion. We'll get into that later on. That's called kinetics. So the position of a particle is often defined by the variable r. The velocity is a v, and the acceleration is an a. But what's really important in kinematics is that all of these variables are vectors, and so we denote them with arrows on top. So position, velocity, and acceleration are vectors, which means they have a magnitude and a direction. So the way that you define that, so we'll start with position. Position is the distance measured from the origin to a particle. So you set an origin, let's say we'll set an origin here, and let's say we have a particle that's traveling along this path called s. So we'll say s is a function of time, and this is the path of our particle. And so s is this path here. Now, our position vector r is going to be the distance from our origin O to the path that the particle is traveling. So we have an actual particle here that's traveling along the path S. Our position vector r is this blue line from our origin to the particle. Now when you get a new problem, it's often up to you to set the origin. Sometimes it's really obvious where the origin should be, sometimes it's less obvious, but that you have to make sure that you're setting an origin O. In this case, it's starting here. So because, and the reason why this is so important is because if I set the origin, let's say I set the origin way over here, my position vector is different because the reference point for that position vector changes. So that's the position vector is r. I'll just do this in a little box. Position vector r, which would be a function of t. Now, for velocity, for displacement is the change in position. Displacement is also a vector. So let's say we have the same path S, so we have the same path here, S, and we have the same origin here, our origin, and our particle is moving along here. So at the first point, our particle, the position will be r of t, and let's say our particle keeps moving along this path here, and then after a certain amount of time, it's here. Now, we'll call this second moment r prime. So now this is the position prime. So this is the position 1, and then this would be position prime. So the displacement will actually be the change here. So this would be our delta r t. So if we write this out, our new position, r prime of t, is equal to where our particle was initially, r of t plus the change in position delta r of t. Now our displacement is the vector from the original position to the new position. And so our displacement is not always the distance traveled. It is the vector that connects P1 with P2. So in this case, you can see that the vector that's connecting these points is not exactly the same as the path that's connecting those 2 points. Now, the distance traveled is what it sounds like. It's the actual distance that that particle travels. Distance is a scalar, so it's not the vector, and it represents the total length of travel. So a more obvious example of this really quick would be if you have, let's say you have P1 here and you have P2. So this is the first position and the second position. If you have a particle that goes like this to get from P1 to P2, or you could have a straight shot here, then your distance would be this piece here. You'd be looking at the actual path traveled, and here your displacement would be that straight line that's connecting them. So if you have units for both position, displacement, and distance, the units will be meters or feet. So if you have centimeters, millimeters, inches, it's very likely that you have to convert them into either meters or feet for your units to work out. This becomes really important, especially when we get into kinetics. So now let's look at average velocity. Average velocity is so V average is equal to the change in displacement divided by the change in time. So this could be delta V divided by delta T. Now just keep in mind here that we have displacement here, not distance. If we want instantaneous velocity, then we take the limit, just like we did when we reviewed our calculus. So then our v, our instantaneous velocity, is equal to the limit as delta t goes to 0 of, oh sorry, I have a mistake up here. This should be this should be, oh my goodness, the change in displacement r. So then the limit as delta r over delta t, the limit as delta t goes to 0 is now dr over dt. And now we're looking, now here we've got a derivative here. Now what is the direction of that velocity? So if we have the path of the particle here is the same, this velocity vector depends on the displacement vector, and the displacement vector was the vector that connected two positions. So if this was position 1 and this was position 2, the displacement vector connected them. Now, as delta t decreases, it means that the distance between the two particles is decreasing. So now P2 isn't there anymore, now P2 is here. If delta t gets even smaller, then the distance has decreased even less. And then the distance increases even less. And the smaller that your delta t gets, this displacement vector becomes tangent to the path of motion. And so the velocity vector is tangent to the path of motion. Speed is not the same as velocity because speed is equal to the distance traveled over time, which would be the actual path. So we had defined the path as s, so it would be the delta s over delta t. And if you wanted to take the limit of that, you could say ds over dt. So if you had the equation for the path of motion, so you had the equation s of t, for example, if you took the derivative of s of t with respect to time, you would end up with that speed. The units for velocity and for speed would be, units here would be meters per second or feet per second. Now, for acceleration, acceleration is the change in velocity with respect to time. So your average acceleration is equal to your delta v over delta t. If you want the instantaneous acceleration, you would take the limit. So then your acceleration instantaneous is equal to dv over dt. Now you can also rewrite this because we know that velocity is dr over dt, then we can rewrite the acceleration as the second derivative of r. So acceleration is also equal to d squared r over dt. So it's also the second derivative of that position vector. The direction for the acceleration vector is a little bit more complicated. It's not just tangent to the path of motion, and we'll get into that in a little bit more detail when we do curvilinear motion, because that becomes a lot more important then. But in the meantime, the units for acceleration will be meters per second squared or feet per second squared.